So good morning, everybody. We are José and Chaouki, and we are very happy to be back here in Hack in Paris this year. Today we will present you the continuation of our research on voice command injection and intentional electromagnetic interferences. So we work for the French Network and Information Security Agency, and we belong to the Wireless Security Lab. Our main focus are on electromagnetic threats on information systems, radio communication security, and we also like to look at embedded systems and do some signal processing. So today we'll start with a short reminder on how voice command interpreters work. And we will recall the work we presented at Hack in Paris last year about the first technique for injecting voice commands into smartphones through the headphones. And then we will present a new injection technique exploiting backdoor coupling. So we will start by presenting our experimental setup and then the exploitation stage. And we will finish with a short conclusion. So voice command interpreters are a user interface which allows a user to interact with his device hands-free, only with the voice. And it's widely deployed in a lot of kinds of devices, such as smartphones or smartwatches. All the main editors or phone manufacturers develop their own solution. So for Microsoft, it's Cortana. Apple developed Siri. Google, it's Google Voice Search, which is integrated into Google now. And the third-party manufacturers that like to deploy a proprietary layer on top of the operating systems also provide their own solution. So here for the example, it's the Samsung solution, which is called S-Voice. And one very interesting point is what you can do using the voice command interpreters. You can first use communication services. So you can place calls, send text messages. You can use internet or connected services. So you can browse the web. You can post and interact on social networks. And you can send emails and so on. You can also do some stuff locally on the phone. You can launch applications, for example. You can interact with the system, and depending on the operating system, you can also personalize or change the phone's settings. So what's new this year is that the editors provide now APIs, or they are starting to do so, to allow third-party application developers to integrate and support voice interaction inside their own application. So this widens the scope of what you can do using your voice to interact with your phone. And another interesting feature is the voice recognition, which can be used and set up to unlock the phone, so to authenticate the user to the phone. A short word on the processing, how it works. So there are both local processing and remote processing. The user, to interact with the voice interpreter, has to pronounce a keyword. So here in the example, it's OK Google. And this keyword is processed locally on the phone and recognized and detected locally on the phone. It activates the voice command interpreter, and then the user can pronounce the command he wants to see executed on the phone. The command is sent to a remote server, which will do the speech recognition, interpret the command, and then send a payload to the phone to trigger the command. An important point is the activation of the voice interpreter. Depending on the settings the user chooses, the voice interpreter can be always active, so always listening to the user voice and tracking for the keyword. Or it can also be restricted, and in that case, the user has to launch the interpreter to be able to interact with the phone by voice. There is a third case. The user can also usually press a hardware button. So this can be the home button, for example, on the iPhones. And it can also be the headphones remote main button. So along with the activation, another important point is the authentication. And the authentication depends on the settings that the user chose. And of course, the OS, the operating system, and the version of the voice interpreter application. Today, many manufacturers or editors propose the user to use voice recognition to perform the authentication. And we will talk about it a bit later in the presentation. And it is possible to limit the commands that are available through the voice interface before authenticating the user and after authenticating the user. So for the example here, I show you the Google settings. So the default setting is not shown here, and the user can interact with the voice interpreter by launching the Google application or from any screen where the Google application widget is present. But then we see that the user also can choose 3 other settings. The from any screen setting, which allows the user to use the voice interface when the screen is on or when the device is charging. The always on allows the user to use the voice interface when the screen is on or off on very specific devices. In that case, I think the voice recognition is already implemented or performed, but it's not used for authentication. So if the user wants to access restricted commands, he still has to authenticate through the PIN code or whatever the authentication method he chose. And then we have the trusted voice, which is clearly an authentication by voice. So you can say, OK, Google from a secure lock screen, and they are able to recognize the sound of the voice, and it unlocks the phone. So we wanted to discuss, to show some recommendations we proposed last year on voice command interpreters, and discuss here with you what changed 1 year later. So the first recommendation we made was to allow the user to personalize the keyword so that it's not always for everyone, OK Google or Hey Siri. And we saw that this feature that was present last year on the phones that we tested is not present anymore, at least on Google and Siri. It's still present for S-Voice, for example, so I think it's a good thing, because it makes the attack a bit harder for an attacker. We also asked for being able to choose the available commands, especially the sensitive ones, and choose if they would be accessible before authentication or after authentication. In that case, the user does not really have the choice, but the editors choose some application for the user. So some privacy-critical commands are restricted and need an authentication or require an authentication, while some other commands like web browsing are available without authenticating. Well, we also wanted to limit the critical commands available through the voice interface, and this obviously will not be the main trend because the editors want to extend the possibilities of this interface. We suggested to use voice recognition to make it harder for an attacker to exploit the voice command interpreters. And in that case, the voice recognition is not really mature. So the feature is available, the user can choose it, but it's not reliable enough to be satisfying. We recommended to enable feedbacks and maximize the possibilities. So today, when you execute a voice command, generally you have a sound feedback and a vibration. And this is good for the user to know that a command is being executed. And we also would like to have finer grained settings to be able to choose which applications we expose and even which features inside the applications we expose pre-authentication and post-authentication. A word about the security state of the art. We already covered that last year, so we will only focus on the new things. So every year there is an authentication bypass on iOS by using Siri. This year there were several. The main idea is to use the voice interpreter to access an available command that is accessible pre-authentication, and then from inside this application, try to fall back to other applications that are restricted. On the local attacks, there has been very interesting research about using audible commands, playing audible commands to the audio front end of the smartphone, but obfuscating these commands so that the user cannot understand the sound, but the speech recognition engine is able to reconstruct the speech and still execute the command. And of course, we presented last year our technique on a remote and silent voice command injection using smart IEMI, which will be described here now by Chaouki, please.
Good morning, everybody. Okay, it's okay. Thank you. Though last year we presented a remote and silent technique for inducing voice commands into targeted smartphone, I will just start with a little sum up of this talk, just for you to better understand what we did last year and how we work. We went further on the technique to describe a new injection attack vector. Though basically last year you already may have seen this picture. We were using a transmitting antenna and we were targeting headphones connected to a smartphone. Though basically we were able to induce the electric signal containing audio voice commands and to get them executed by the targeted device. We also presented a different scenario in which we may be using this kind of attack vector. So basically the tracking scenario, in which we described that we were able to turn on a wireless interface of the targeted device, and then we could be able to check if someone is around the system to attack the target. Eavesdropping scenario, in which we have shown that we were able to place a phone call to a specific number and turning the device into an eavesdropping system. As we were able to place phone calls, we also discussed the cost abuse. So basically, we could also place phone calls to overpaid services. We also talk about reputation and phishing attacks. So basically, if we are able to send Twitter messages or text messages to anyone, we could make some bad things on the reputation of the targeted guys. We also discussed the malicious app triggering by using specific audio voice commands and to make this application download some payload to put some add-ons on this malicious application. We also talk about advanced compromising of the target. So basically, we discussed the fact that we were able to turn on a wireless interface. And based on this, we could be able to emulate an access point for attacking the Wi-Fi interface of the targeted device. So that was the scenarios we discussed last year. But we also discussed the limitations of the attack presented last year. So basically, there were minimum required fields around the target. So it was 28 volt per meter at 100 megahertz. So this means that if we want to build the source to perform the attack of last year, it required an amplifier of 40 watt for attacking device at 2 meters. So we may imagine a guy working through a crowded area. And to reach targets at 5 meters, then we needed an amplifier of 200 watt. So this makes things very difficult to use. Though the main limitations of the test of last year was that it required the headphones to be connected to the smartphone. The distance between the source and the target was limited by the minimal required field. And it also was highly dependent to the activation conditions. So we have shown that we were able to trigger, to emulate the hardware press button on the headphone. And also, it's highly impacted by the settings of the users. Though we wanted to check if it would be possible to overcome these limitations, and we just decided to go further and try another attack scenario by reading the descriptions of editors and manufacturers, providers of voice command interpreters. We have seen, interestingly, that you are able to wake up your smartphones with the voice commands and the keyword when the device is connected to the power network. So this means that devices, when they are charging, allows the user to interact with it and make some specific command to be executed on the target. So it's, for us, the target, but it's in its own smartphones. Though this brings us to the topic of today, which is basically try to analyze if we could be able to interact with devices through when they are connected to the power network through the USB cable. So this is the target of today. So just a few words to make things clear for you. There are two propagation modes, so the radiated one and the conducted one. So the radiated one, one can just imagine a communication between two radio communication systems, so antenna to antenna communication. And the conducted propagation that you may already use at home for home networking through power line communication systems. So, and we will focus on the conducted propagation mode today. Another thing about intentional electromagnetic interferences, we describe two kinds of coupling modes. The first one is when inducing signals into an antenna. We call this the front door coupling mode. And when we are able to induce electric signal into conductive parts of any electronic device, which is not designed to receive signals, then we call this backdoor coupling. And this is the topic of today. So the propagation mode is the conducted one, and we try to exploit a backdoor coupling phenomena for trying to reach targets. Here we have an example of a target, so it's a Samsung Galaxy Nexus. We have the charging port part on the PCB, where we can see on the right the point of entry for us for our parasitic signals, so it's the USB connector. And what we would like is to be able to couple electromagnetic signals by entering the signal into the USB cable and to reach the microphone IC, which is on the left. So just to remember you what's a USB cable, we all know that you may all know what it is. But we have 4 wires, 2 for the power, the red and the black, and 2 for the data transmission, which are the white and the white and the green. And what we would like is to use this cable for inducing our signals into the system, and then trying to interact with the microphone IC. So there are 2 phenomena that may occur on the PCB, which are the bypass of the isolation between the 2 hardware components by parasitic coupling. And also another interesting point is that on some PCBs, the 2 electronic components are sharing the same power network, even if they are some isolation components, so conductor and capacitors. But let's try to interact with this. In order to test this backdoor coupling mode attack vector, we need some specific devices. We replaced the antenna with an injection probe, so on the left, which is something we can buy on the web. And also we designed a homemade coupler, so it's the power part on the power line communication modems. And we will try to plug this into the power network for testing our injection technique. The signal injection of last year was highly presented. I will just give some words about that. We placed smartphones with their headphones connected into a Faraday cage for regulation purpose. We had an application to stream the audio input of the device streaming to a monitoring computer, and we were generating our signal with a USRP. And we have demonstrated that good coupling frequencies for injecting voice commands into smartphones were in the 80-100 megahertz frequency band. So we removed the antenna and the headphones, and we connected the devices to the power network with the power charger into the power socket. And we used our injection probe and also our malicious coupler. And we are still using our USRP and trying to reach devices for the power network. And we have seen during the preliminary test that a good coupling frequency was 218 megahertz. So, as we may imagine, injecting signals into the power network, the electromagnetic interference has to propagate into a propagation channel, which is composed of the power cables, the USB chargers, the USB cable, and then the coupling between the USB connector and the audio microphone IC. So as a preliminary test, we wanted to test several USB cables. So we placed the targets directly connected directly to the instrumentation for our USRP. And we used, you can see here there are 2 USB cables. So we compared the USB cable with data link and the power cables, the charge-only cables. And we characterized the frequency band, the audio frequency band of coupling on the device. So we are still looking to the signals induced on the target by using a free available application called Wireless Mic. And we can see here the frequency domain analysis of the induced signal. So comparing the 2 cables, here you have the frequency domain, the spectrogram here. This is the induced signal, which is a sweep, which allows us to estimate the coupling frequency band into the device, composed of the voice frequency band, the audio frequency band, and the ultrasound frequency band. And you have here the 2 frequency response of the cables, and we have seen that depending on the used cable, the audio signal is degraded in different ways. So here we have a high difference between the effect for the low frequency and also some differences on the highest frequency. Then we used our target. We connected our target to the power network. Here we have the power, the charger connected to the power network. You have our injection probe and the malicious coupler. And here you can see the frequency response when injecting the signal through the power network. So as a preliminary results, we had interesting injection results. Basically, we were able to induce audio signal to the power network when devices were charging for the low voltage network. We also connected our devices with the USB to a computer, and we have seen that we were also able to induce audio signal through this setup. So then we went, so the first question is, are those signals interpretable by the voice command interfaces? And another interesting result was that the required power for injecting the signal was less than 500 milliwatt. And the second question is it enough to get voice signal interpreted and command executed by the targets? And then José will show you the results.
So at this step of the research, we know that we are able to interact with the audio input interface of the phone by injecting our parasitic signal into the power network. And now what would be interesting would be to verify if voice command interpreters tolerate the signals that we inject and interpret them as commands. So we considered 3 scenarios, and they differ in the point of injection and the different filters that our parasitic signal will go through to reach the target phone. The first scenario is the classical one. The phone is charging through the power network with a genuine USB charger. The second scenario is the phone charging on a USB port on a computer, which is connected to the low voltage network. And then we imagine the third scenario, direct injection through a malicious USB charging device, which is an interesting scenario because there are less filters on the propagation path between the injection point and the target audio front end. The first scenario is the most classical one. We all have that at home. We have a USB charger that we connect on the power network. And in that case, our parasitic signal will have to bypass the transformers that are inside the USB charger and bypass the high-pass filters that are in the charger to discard the 50 hertz of the power network. And of course, we would like to know if the audio quality is good enough to be processed by the voice command interpreters. So for the demonstration here, we have 2 setups. The phone is connected to this power strip with a genuine USB charger, and we will inject our parasitic signal whether with a coupler on the same power strip or directly inside into the power strip cable with our injection probe. So in this video, on the power strip, we also have a computer connected, and this will allow us to check if the computer is disturbed by our injection or not. So we see the setup, and we inject the parasitic signal. The keyword is recognized, and the command, which is démarrer Gmail or start Gmail application, is well interpreted by the voice command interpreters. The second scenario is a bit trickier. The phone is charging through the USB port of a computer, and the computer is connected to the power network. And here, the filters, the main signal filtering elements are inside the computer. So the point of injection is the same as in the first scenario, and the signal will have to bypass the transformers that are inside the computer's power unit and the high-pass filters of that unit. And of course, the same assumption or goal that we want to reach is a good quality so that our command is interpreted and executed. And we don't want to disturb the computer. So here, on the right, it's just a picture of the back of the computer, and we highlighted the injection probe and the USB cable. So the phone is connected to the USB port of the computer. And we see that we are still able to forge a parasitic signal, induce it inside the power network, and it goes through the power lines or inside the computer and propagates to the target phone. And the third scenario is the custom malicious charging device. So it's a typical scenario where the target will charge its phone on an unknown charger. Sorry?
Untrusted.
Yeah, untrusted. Yeah, thank you. Charger. And here, for the attacker, there are less problems because there are less filters in the propagation path of the parasitic signal. An interesting scenario would be to have a malicious charger that will try to identify the target. So sometimes the cable shape is a good clue. And try different frequencies until it can hear or catch the feedback of the keyword recognition. Once the charger hears the feedback or catches the feedback, it knows that it was the right coupling frequency, and it can exploit. So for the demonstration here, we didn't build a malicious charger. Instead, we inject directly in the USB cable between the charger and the target phone, so that our parasitic signal does not go through the filters of the charger and goes straight directly into the audio front end. So we see our setup, and as always, the keyword is recognized, and the command is executed and interpreted by the phone, the interpreter services. So the results of our experiments, we successfully injected voice commands silently from the power network through the charging USB cable to the targeted phones. Directly from the power network through a computer when the phone is charging on a computer, and the audio signal is processed correctly by the remote servers, and the command is executed. We didn't notice perturbations on the computer or the peripherals that were collocated with our target, and sorry. We also didn't really see an impact of the different types of USB cables. I mean, the charge-only or the regular USB cables for the injection. However, there are some main limitations that make this attack very high attacker profile attack. The first one is the power network topology and the different devices that are connected on the power network. These criteria can change a lot the modifications or the perturbations of the parasitic signal between the injection point and the target. The second point is all the filtering steps that we mentioned. So in order to have a successful attack, it's mandatory to characterize the chargers, characterize the computer filters, for example, in order to be able to forge a signal that will have a good enough quality to be interpreted by the voice interpreters. And the third point is the target phone, because the phones are different and the PCB characteristics are different. And the topology of the PCB can also play a huge role in the last step of the attack, which is parasitic coupling between the power interface, which is the USB port, and the audio interface, the entry stage of the audio front end.
Okay, just to conclude this presentation, we will just remember, sum up the presentation. We have been able to reach targets at a longer distance. So the power network is a very good propagating structure for electromagnetic waves, and that's why we are using them for power line communication system. The power required to reach targets and to get signal induced and executed by the device is less than 500 milliwatts, which is very a small amount of power. The source can have a limited size, so basically a malicious PLC transceiver is enough to do the test. It's also interesting because we can directly grab the power for the system on the power network as we are connected to it. There is no more need for headphones, and basically all targets, those devices that are charging may be reachable targets. Just to compare the two techniques, so the talk of last year and the talk of today. Last year we were focusing on the frontal coupling mode. The propagation path, the attenuation in the propagation path was directly related to the free space attenuation. We needed the headphones to be connected to devices, and the required power were 40 watt for 2 meters and 200 watt for 5 meters. And the source size is depending on the type of the source and the distance we would like to reach targets, is a backpack or a car. And targets were devices outdoor in the street or in crowded area. And today we have been discussing the conjuncted propagation path, where we were focusing on the backdoor coupling mode. The propagation path is the power lines, the power network, which has a very small attenuation at the frequency we were working on. The required power is 0.5 watt, and you were able to reach targets at a distance higher than 10 meters, which is much better than last year. And the source size as well was a small PLC charger, which is something interesting to target indoor devices charging for the power network or a computer. So we discussed the front door and the backdoor coupling phenomena, and we have seen that we were able to remotely and silently inject voice commands into targets. Again, so we wanted to discuss the threats of electromagnetic interferences as an efficient attack vector against IT systems. It's no more limited to denial of services attacks, and they are more and more affordable as we may build low-cost with software-defined radios. We need to take this into risk analysis depending on the critical infrastructures we have to protect. And also, again, so carefully choose voice command settings as soon as we are able to make very specific settings. I will do it quickly. Voice command interfaces are evolving, so default settings are more and more secure. Nevertheless, more activation options are provided, which may be new attack vectors to try to overcome some limitations. Voice recognition is now available on certain devices. The authentication and unlock is mandatory for some critical commands, especially for privacy reasons. But it also increased the scope of possible actions we may do on the devices. Users get used to it and will slowly move away from security toward usability. Also, the voice recognitions cannot consider as mature enough today. Just for ending the talk, José will show you something about this.
Yes. Yes, just a word on the voice recognition of authentication. We run some tests, and we have a little demo for you to end the talk. The voice recognition on the keyword is not really mature yet for authentication. The first point is that only the keywords are analyzed, and the keywords are generally short, and as we saw, they cannot be personalized, so it's always the same. And the command is not, the voice recognition is not made on the command. So there is a simple audio replay attack example, which we will show in a few seconds. And the scenario is the attacker will try to get voice samples from the victim. This can be quite easy to get someone say OK and then Google on the phone, for example. And then to forge the keyword and play it to unlock the phone. So it can be played through speakers, which we did in the demo, but it could also be injecting with the two techniques that we presented this year and last year. I would like to mention that the editors are aware of that weakness, and they warn the user that someone with a similar voice or a recording of the voice can unlock the device. So trusted voice recognition for authentication is considered less secure than a PIN or a password. So I hope the sound will be okay. So here the target phone is unlocked. I'm going to lock it. So now it's locked. It's prompting for the PIN code. And now with the second phone, we are going to play. No sound. Oh, sorry. Maybe we can do it. Okay. Like that. Okay, so for the trick, we recorded my voice for the keyword and then Chaouki's voice for the command.
Okay, Google.
Open Gmail.
And now the Gmail application is open, but the phone is also totally unlocked. So we do not recommend using voice recognition for unlocking the phones for now. Thank you very much.
Thank you.
As usual, all the references are in the slides, so if you are curious about the state of the art of the security of the voice commands, you can go on. And our emails also, so if you want to reach us to ask questions or to do research together, don't hesitate. Thank you.
Thank you.
Sorry, me again.
Hello.
Hello. Okay. Maybe it can be easier if I stand up. So Amanda Gabiam from Trusted Labs.
Yep.
Since you mentioned the talk was really interesting, and as we talk about electromagnetic interferences, I was wondering if you performed some tests on NFC-enabled or BLE supporting devices.
Some tests on, sorry, NFC?
NFC-enabled devices,
Yeah.
and those who support also BLE, Bluetooth Low Energy.
Yes.
So I mean, concerning the result actually, because since it's waves, interferences, you saw some demo about voice recognition. Did you notice anything about these devices? Because there are, I mean...
Your question is not really related to the voice recognition, or...
Actually, mentioned at the beginning about electromagnetic interferences and waves.
Okay. Yeah.
So it was more on that to see if you can make the scope larger and exploit using NFC features.
Oh, sure. Maybe we can talk a bit about the max spoof.
It will be nice. Thank you.
You saw the max spoof attack?
No, actually, I didn't see the previous year.
No, it's not.
Okay, so...
Yeah, it's a Samicam car that built a small device that was able to induce an electromagnetic or an electrical signal using electromagnetic interferences into max stripe readers.
Yes.
So that was this year, and it was quite interesting research.
Okay, so
yes, the answer is yes. It's an interesting research topic, and it might be. I think we can do a lot of things with intentional electromagnetic interferences.
So actually, NFC-enabled phone may be more vulnerable?
We cannot provide you an answer about that topic because we didn't work especially on NFC-enabled devices. Okay. We have been testing devices in order to understand what are the threats for the audio-voice interface. We also have been testing devices against electromagnetic threats, and it's an undergoing work today, so we could not provide you very specific results. But as said, José, we can just discuss this a few later if you want.
Okay, it will be nice. Thank you.
Thank you.
Thank you.
Oh, there's a question in the back.
Thank you. Firstly, thank you for the amazing demonstration. It was fantastic. I have a question about, say, if you wanted to have a booth with multiple USB chargers, would you need separate couplers, or is it possible just to broadcast through multiple cables at the one time on repeat, you know, cycling through Apple, Android, and so forth?
In fact, we have been working a lot on the power network, and we have seen that depending on the type of the charger and devices connected to the power network, the signal will be degraded, so disturbed by the impedances of devices. But if there are several devices, we need only to characterize many chargers and then understand which one may be used for each device, and then try to define a specific coupling frequency, and also using some statistical techniques to target specific adapters on the power network. So the limitations of the topology, as said José, is something very, very hard to overcome. But there are some techniques we have been working on in order to overcome those challenges. I think it's time for the coffee break if there are no more questions. And we can just talk up. Sorry.
Okay. Thank you.
Okay. Thank you.
Thank you very much.
Thank you.